Hi, I'm Nick Donnelly and welcome to the third part of this series of presentations put together by the New Zealand Institute of Surveyors positioning stream, the University of Otago and Land Information New Zealand. This series is about the New Zealand Geodetic Datum 2000 deformation model. So in this third part, what I'm going to focus on is a little bit more detail about some of the tools that are available to help you use the deformation model. And I'll go through some examples of the sorts of calculations you can do to get an understanding of how the deformation model might impact on the work that you're doing. So I'll briefly cover the range of tools we have for dealing with deformation. I'll run through an example of assessing the impact of the deformation model using one of those tools, which in this case is the online coordinate converter. I'll talk about accounting for deformation using the LINS provided SNAP software, and I'll also talk briefly about a tool that can be used for more advanced analysis if you have a need for it. So if we have a look at how we can do calculations using the deformation model, there are a few tools available, and what you choose to use really depends on what it is you need to do. So there's a table on this slide and the next one which highlights some of the main purposes that you might have for using the deformation model. So for example, if you want to update your Geodetic Datum 2000 coordinates using a reverse patch, so for example maybe you're managing a database in an area that was affected by the Canterbury earthquakes and you want to apply a patch to account for that deformation model, then there are GIS grid files and software available, the likes of ArcGIS or GDAL. There's a link there on the LINS website where you can find more information about how to go through that process. If you're wanting to transform coordinates between the Earth-fixed global reference frame and the plate-fixed GD2000 datum or reference frame, you can use the web converter on the LINS website, which is currently still in beta version, but you can use it. There's a link there to it. And we also have the Concord software, which is included as part of the SNAP download. If you've got some survey observations, perhaps spanning a reasonably large length of time, and you want to calculate NZGD2000 coordinates, you can use the SNAP software for that. And if you're wanting to carry out more specialised deformation calculations, so for example, maybe you just want to know the displacement due to a specific earthquake, then there's a Python program that's distributed with the deformation model. So that does require installation of the Python environment on your network or on your computer before you can use that. But again, with that software, there is documentation to help you use it, and that's all downloadable from the LINS website at the link provided there. So now we're going to have a look at an example using the online coordinate converter. And the link is given there. Because it's still in beta version, at the moment in September 2015 when I'm delivering this, it's not quite on the live website. So if you go to that link and it's not available there yet, you can just use the link there to the coordinate converter test website and that will get you there. So the scenario that we've set up here is we've got a project area that we're interested in and we want to estimate the impact of deformation on that project area by comparing some Datum 2000 coordinates with today's ITRF 2008 coordinates. So ITRF is the latest version of that global reference frame, and by today's date, specifically, I'm meaning 2015.589, which happens to be the 3rd of August. So if we have a look at our project area here, I've selected Wellington City, and the reason I've selected this area is because it's a major urban area but it's also in an area where there are very high strain rates compared to other parts of New Zealand. So this is the sort of region where we are potentially expecting to see some significant deformation. So the purpose of this exercise is not to do a robust analysis of deformation throughout Wellington. What we're wanting to do is get an indication of what the deformation is, so that we can use that information to decide, firstly, do we need to apply the deformation model? And secondly, what is the general magnitude of those corrections that might need to be applied? So to do this analysis, we're just going to pick some points at the extents of our project area. And so I've just picked a point at each of the north, east, west and south extents. And you can see there in the table, I've provided those coordinates in terms of datum 2000, latitude and longitude, decimal degrees, and also converted into the Wellington meridional circuit projection, just to make some of the interpretation of the analysis a little bit easier later on. So looking at that graphically, again, you can see all we've done there is picked 4 points at the outer extents of our project area. So these next few slides are going to show how you can set up the online web converter. So this is on the Land Information New Zealand website. So the first thing we want to do, if we're converting these coordinates between NZGD2000 and ITRF, is provide the converter with details of our input coordinate system. So in this case, it's datum 2000. So the input coordinates are just going to be those ones I showed in the table before. So that's the NZGD2000 latitudes and longitudes. And there's various formats that the converter can take. So I've just chosen the coordinate order and format that matches the way that I wish to enter my coordinates. We don't need to worry about a height in this case. We're only looking at horizontal deformation in this exercise. The next part of the setup is to provide details of the output coordinate system. And in this case, I've chosen ITRF 2008 as the most recent version of the global reference frame. Again, there are various options there for the format of your output coordinates, so you have some flexibility there in terms of what you might want. Finally, we need to put in some conversion options, and perhaps the most important one there is the top one, which is conversion date. And that might be something that you haven't used before, doing coordinate conversions, because for many coordinate conversions it doesn't matter what date you do it at, the answer will be the same. But because this coordinate conversion does involve use of the deformation model, and deformation is time dependent, so that just means deformation after 1 year might be 5 centimetres, 2 years it's going to be 10 centimetres. So we need to know the date of the coordinates we're wanting to convert so that we can do those conversions. So there's a couple of options for how you can enter that conversion date. You can see on the slide I've just written now, and that will pick today's date to do the conversion at. But if, for example, you had some, or we wanted to get ITRF coordinates at a date that wasn't today's date, then we could put the actual conversion date in there and it would do the conversion for that particular date. The rest of the options there just depend on what you want in terms of the input and output formats, precisions, and a bit of options there to put codes in associated with the points that you're adding. So we've got everything set up. We then enter our 4 coordinates and do the conversion. And this is what we get as output. So what you can see there is that the International Terrestrial Reference Frame coordinates are very similar to the NZGD2000 coordinates. It's really just down in some of the further decimal places that there are differences. And we would expect them to be similar because overall New Zealand is moving at about 5 centimetres per year. So between 2000 and 2015, we would be expecting to see maybe 75 centimetres of movement. So we are expecting to see something, but we're not expecting it to be particularly big. So what I'm going to do now is just use those sets of coordinates, so the input GD2000 and the output ITRF2008, to do some calculations. The software that can be used to do these calculations, any kind of survey software, GIS software, even a spreadsheet would be able to do it. So we're not doing anything, I guess, particularly tricky here, but we're just trying to get an indication of what the general magnitude of the deformation is. So for this first bit of analysis, what I'm wanting to do is compare those NZGD2000 coordinates and those ITRF2008 coordinates in a form that's slightly more useful to this output format. We're looking at those latitudes and longitudes. Unless you're very familiar with how those convert in terms of meters, it doesn't really give you a very good idea about what the magnitude of the deformation is. So all I've done is I've loaded up each set of coordinates, and in the first two columns of that table, which are labelled ellipsoidal distance and projection bearing, I've just taken out the inverse, the bearing and distance between the datum 2000 point and the ITRF point, and that's what we get. So we can see there that it's about 0.65 of a metre, and they're in roughly the same direction. And so that ties in well with approximately what we're expecting to see based on 5 centimetres per year. Then in the change in east and change in north columns, I've just converted those distances and bearings into metres there. And that gives us our first indication in the east and north change columns of what the range of deformation values are across this area. So just by scanning your eye down the east column, you can see there that there's a range of about 15 centimetres in the easting, and in the north there's a range of about 5 or 6 centimetres there. So for many applications, that's a level that is potentially going to be significant. So the deformation is not identical at all 4 points of our project area. So that's the first thing we can take from that. Now what I'm wanting to look at in a little bit more detail is what the effect might be on the relative accuracy of our project area, because that's usually what we're interested in. If the difference between datum 2000 and ITRF, if it was consistently, if it was the same in all cases, then it probably wouldn't be too much of a problem, even if it was really large. If all 4 of those points had all moved by 100 metres, that would actually be fine, because relatively all the measurements you make would agree with those coordinates, and it's that relative accuracy which is generally of most interest. So what I've done here is I've taken the difference between the north and the south GD2000 point, the north and the south ITRF point, so that's providing 2 vectors, one in terms of GD2000 and one in terms of ITRF. So what we get when we do those calculations in the table, see the change in east and the change in north for each one, and then I've done the difference between them. So in the east, the difference between those 2 vectors is about 14 centimetres, and in the north component it's about 7 centimetres, for a total difference of 16 centimetres. So another way of thinking about what that means is if we'd gone out on 1st of January 2000 and made a measurement with GNSS of a vector that was about 33 kilometres long in that direction, we would have got a value, a distance for that line. If we went out today and measured that same line with GNSS, due to deformation, it would be 16 centimetres different. So that gives an indication of the extent of deformation across the Wellington region in the north-south direction over 15 years. Doing exactly the same calculations in that east-west direction, going through the process, we find that in this case, the difference between GD2000 and ITRF is about 12 centimetres over that 16 or 17 kilometres. So again, for a lot of projects, that is going to be of interest, it is going to be significant. So by going through that exercise, we've seen how to use the coordinate converter, and we've also seen that in this case, the deformation is something we're potentially interested in. So let's move on with the example and say that actually we are looking for better than 10 centimetres in this job, so we definitely need to be applying the deformation model. So what I'm going to talk about now is how you can use some LINS provided software to account for the deformation model, and that software is called SNAP, the Survey Network Adjustment Program. So the nice thing about SNAP is it correctly applies the deformation model to calculate GD2000 coordinates by default. So it's very well set up for doing these sorts of calculations. It is important to make sure you've downloaded the latest version of SNAP from the LINS website. And one of the reasons why that's particularly important in this context is the deformation model does get updated periodically, both due to earthquakes and also because we update the long-term secular model because of more information. So you'd always want to be doing your calculations using that latest version of the model, and by downloading the latest version of SNAP you can be confident that that indeed is what you're doing. For those of you who are not familiar with SNAP, it works based on text files to input the data, and I've just shown some examples of those text files there. There's extensive documentation associated with the software, so if you're not familiar with it, you can have a look at that. But what I've got there is, the first one is a command file, and all that does is provide some references to the other files that SNAP needs. And also in this case I've told it to hold fixed two stations, which are WGTN and BDPD. The coordinate file provides a list of coordinates that are going to be used by the software to do its calculations. So if they are coordinates that you're going to want to hold fixed in your least squares adjustment, they need to be the best coordinates that you can get. They need to be high quality. If they're coordinates you're wanting to calculate, then they just need to be approximate. The final SNAP file is the SNAP data file, and that's where we put our observations. So in this case, because we're doing a very simple exercise here, there's just a single observation between two geodetic marks, WGTN and BDPD, and those are the X, Y and Z vector components that we've measured. And you'll notice, very important here, and indeed essential in this case, is the date of that observation, because without the date, the deformation model cannot be applied. So just to have a look visually at what we're doing, we've picked WGTN, which is a permanent GNSS station at Wellington Airport down in the south of the city. And then we've picked a second mark up in Tawa, which is BDPD. Now, both of these are existing geodetic marks, so they already have good geodetic NZGD2000 coordinates on them. So we're going to use those good coordinates that we already have to have a look at some of the impacts on deformation and how SNAP applies the deformation model to deliver a much more accurate result than would otherwise be the case. The area that's highlighted in red there just shows parts of the city where the relative deformation or the distortion is estimated to be more than 0.5 parts per million each year. So on this slide we see a couple of outputs from the SNAP software. In the top screenshot, this is an example of not using the deformation model. There's various bits of information there, but the one that I'd like us to focus on is the final column, which is labelled RES, which stands for residual. So that's the difference between those existing coordinates that we took from the geodetic database for those two marks, and then our measurement that we made in November 2014. And when we hold those two marks fixed and look at how well our measurement agrees with it, we see that overall there's a discrepancy of 89 millimetres. 85 millimetres in the east component, 16 in the north, and 24 in the up component. Now that's more than we would expect for making a high quality GNSS observation over this distance. But again, I reiterate, the deformation model is not used in this case. When we do apply the deformation model, again looking at the residual column, there's a significant change there. And now our overall residual is 32 millimetres. That east residual has dropped all the way from 85 down to 7 millimetres, and the north and the up stayed fairly similar, but still small. So that 32 millimetres is now much more likely to give some representation of what the error of our observation is, or perhaps what the error in the fixed coordinates are, because we have now taken care of the deformation model. So that's a very simple example, just using a single observation. If you were doing a job across Wellington City, or indeed anywhere in New Zealand, you could put all of your GPS observations or any other type of survey measurements you may have made into the SNAP software, and it will calculate GD2000 coordinates using the deformation model so that you can be confident that you're getting the maximum accuracy out of them. So just finally, I'm going to very briefly touch on one of the tools we provide for doing more advanced analysis, and that's called calcdeformation.py, which is a Python program. So it's a Python script that's included with the deformation model that you can download from the LINS website. It's command line type software, so it does take a little bit of getting your head around, but there are instructions provided with it and examples provided with it of common calculations that you might want to do using the deformation model. So in general, you wouldn't be using this software. It's something that LINS developed for research and development purposes, for managing and testing the deformation model, but we make it available because there may be some applications that you find it useful for. So, for example, if we wanted to specifically calculate the amount of deformation between 1st of January 2000 and 3rd of August 2015, that's the command we would use, and there I've shown some examples of an input and an output text file. And highlighted in red there, we can see that for the station Auckland, which is just north of Auckland City, there's been 9 centimetres of deformation in the east component and 60 centimetres in the north component, and 0 in the up component. However, the secular long-term deformation model currently doesn't have any vertical component to it. So even if there were vertical deformation, it would still return as 0 in this case. Just as a second example of something that you might want to do using this software, you may wish to determine the amount of deformation just due to the 4 major Canterbury earthquakes. So perhaps you're not interested in that long-term secular deformation, you're just interested in the earthquakes. So again, that's an example of the command that you would use, and the 4 patches are represented by that C1 plus C2 plus C3 plus C4. Now that syntax is explained in the documentation, but it relates to the way that those earthquakes are represented in the deformation model. And again, there's examples there of input and output, and we can see that for the mark DJMF, which is in Littleton, there's been east deformation of 18 centimetres, north of 24, and in this case there is an up component because the earthquakes, we did model the vertical component of deformation, and that up component is 12 centimetres. So just to finish, I'd like to reiterate a few key points from both this part of the presentation series, but also the earlier ones provided by Chris Pearson and Chris Crook. So ITRF 2008 is the most accurate reference frame or datum available, with coordinates that will change continuously for any ground fixed object. So what that means is that the ITRF coordinates will match your GNSS observations as long as the epoch of the coordinate and the epoch of the observation is the same, even over very long distances. So that's one way of thinking about what we mean when we say ITRF 2008 is the most accurate. However, the fact that the coordinates change continuously, that's often something that we don't want. Therefore, we have NZGD2000, which is far more durable. So that means in this context that the coordinates are stable for a ground fixed object, but it does mean that coordinates may not match observations, especially over longer distances if the deformation model is not used. And that's what we saw in that example from Wellington, where in 2015, across the city, you can be getting up towards 20 centimetres of difference between Datum 2000 and Otago 2008. And finally, the deformation model enables the generation of accurate NZGD2000 coordinates from observations made at any time. So that deformation model is the key link between the global reference frames and the global technologies such as GNSS that are very frequently used, and the stable, durable NZGD2000. And just finally, if you're interested in this sort of material and would like to find out a bit more about it and perhaps a little bit more about the international context of both reference frames and also deformation modelling, associated with the FIG Working Week in May 2016, the NZIS positioning stream in conjunction with FIG is going to be running a 2-day workshop on topics relating to reference frames and deformation models. So that will be targeted at surveyors and other spatial professionals. So thank you very much, and we would welcome any questions that you might have. There are contact details on the LINZ website if you need to get in touch with us. There's also the web links provided there to pages on the website where you can find more information. Thank you very much.